Okay, this video I'm just going to quickly go through the graphs of sine, cos and tan using the unit circle just for one period between 0 and 2 pi, or 0 and 360 degrees. So this is the unit circle, which means a circle with a centre 0, 0 and a radius of 1. So this is the point 1, 0, 0, 1, minus 1, 0, 0, minus 1, and so on. It's a nice circle, right? It's obviously could be drawn a lot better, but hopefully it's good enough so I can get the point across. Right, so generally speaking, you should have seen this in GCSE. You can pick an angle theta. So if we draw a line at an angle from the origin, at angle theta, and then we just extend that line until we hit the circle. Okay, so then that point P will have coordinates x and y for now, right? And then what we can do, we can draw a vertical line back to the axis, and then we can think about this horizontal line. Okay, so what that means is this triangle will have a side length here of x, as in whatever the x coordinate of P is, and this, because it started at 0 and went to x, and the same thing for this, started at 0, went to the y coordinate of P, which for now we're just calling y, right? So if we just write a couple of things down that we know, using your SOHCAHTOA, you should know that sine theta equals opposite over hypotenuse. We do know the value of the hypotenuse. It's a unit circle, so the radius is 1. So whichever direction we go off in, this has a length of 1. So you know sine theta equals opposite over hypotenuse. Opposite is y, hypotenuse is 1, which just equals y. So what that means is sine theta is always the y coordinate. So y coordinate is sine theta, and this always works. In the same way, cos theta we know is cos theta equals adjacent over hypotenuse, so that's adjacent x over hypotenuse 1. So that is x over 1, which just equals x. So that tells us that the x coordinate is cos theta, which means that we now know P, yes, it's at xy, but it also means that it is at cos theta sine theta. Y we can now write as sine theta, that's the y, and x we can write as cos theta. Now if we think about tan theta, well, tan is TOA. Tan theta equals opposite over adjacent, so that would be opposite sine theta over adjacent cos theta. So tan theta equals y over x, which we've said y is sine theta and x is cos theta. So that's one of your identities, probably your second most common, or the second one you come across. Tan theta equals sine theta over cos theta. We've already used it. And for the other one, well, we call it the Pythagorean Identity, because you use the right angled triangle. You can see this right angled triangle here. A squared plus b squared equals c squared. So a squared x squared, or cos theta squared, or actually, if I swap them around, you can add the short sides, or square the short sides and add them in any order. So sine squared theta plus cos squared theta equals 1. Sine squared theta plus cos squared theta equals 1. And that is the most important, most widely used, most useful trigonometric identity. Right? So all of them, both of the first two, come directly from this circle. Right, so now if we think about the graphs, knowing that as we go around the circle, well, we know that sine theta is always the height, then we should be able to go around here quite nicely. So if we just label some angles, we know this is 0. Once we go up to here, well, this is pi by 2. This 180 degrees is pi. Then we have 3 pi by 2. And we have 2 pi over here, same as 0, because we've done a full cycle then. So what we're going to do is just sketch sine theta between 0 and 2 pi. So if we have 0, 2 pi, so that would mean pi is in the middle, pi by 2 is in the middle of those two, and 3 pi by 2 is in the middle of pi and 2 pi. Okay, so that is theta. On this axis is going to be sine theta, which has a maximum of 1 and a minimum of -1. Okay, now we've just decided, or we've just defined sine theta as the height, the y coordinate. So when theta is 0, you can clearly see that the height is 0. So sine 0 must be 0. So we know it goes through there. If we go up to pi by 2, you can clearly see that sine pi by 2 is 1. So pi by 2, we're going to have this coordinate here, right? If we then go along to pi, you can see that sine pi is back to 0 again. So it's here. 3 pi by 2 is down here, where we've got a height of -1. -1 there. And then if we go back to 2 pi, we're back to 0 again. So we know we pass through those points. Now, if we think about what happens in between, well, on the journey from 0 to pi by 2, if we imagine we're increasing the angle at a constant rate, this is quite steep at first. So the height increases quite quickly at first, and then it's on a flatter line, it will increase more slowly. So it's going to increase quickly and then slowly. That's not quite what I was aiming at, but it'll do. Then as we go from pi by 2 to pi, the opposite's going to happen. It starts off flatting, so it slowly goes down, and then it goes more quickly down to pi, down to 0. So it's going to go slowly and then getting steeper. From pi to 3 pi by 2, you can see it's quite steep at first, so the height's descending rapidly and more slowly. So it's going to do something like this. And then for the last bit, it's going to gain height slowly and then more quickly as it gets steeper. So that is the graph of sine theta for theta between 0 and 2 pi. If we do something very similar for cos theta, try and line everything up. Pi by 2, pi, 3 pi by 2 and 2 pi. We have a 1 and a -1, and this is cos theta against theta. Right, remember cos theta is the x coordinate, so it's here. You can see that cos 0 is 1. We're pointing at 1, so it starts here. As we go around to pi by 2, the x coordinate there is 0. So cos pi by 2 is 0. Then we go around to pi, and we are at -1 as far as our horizontal coordinate goes. So down to -1 like that. Come around to 3 pi by 2, that is here. You can see that the x coordinate is 0. And if we go all back up to 2 pi, you can see the x coordinate there is 1. The horizontal bit is 1. Positive 1 up here somewhere, right? So we can see the points we must go through. We can think about, well, how we get there in a similar way. Now we're thinking about what's happening horizontally. So if we're increasing the angle, as in we're turning this thing anti-clockwise at a constant rate, you can see we're not doing much horizontal movements, quite slow at first, and as the line gets flatter, it speeds up. So the cosine is going to increase quite slowly at first and then quicker. So it's going to be like this, down to there. Now if we go from pi by 2 to pi, on a flat line, you can see there's quite a lot of horizontal change and then less horizontal change. So it's going to go steep and then shallow, like that. From pi to 3 pi by 2, it's going to increase not much and then more. So it's going to start off shallow and then go steep. And then for the final part of the journey, you get a lot of horizontal change as we're spinning around, and then less. So it's going to go steep and then shallow. So that is the graph of cosine theta, or theta between 0 and 2 pi. With tan, I'm going to leave a bit more room because it does go beyond 1 and -1. So we can still have our 0, pi, 2 pi, pi by 2, and 3 pi by 2, right? So this is going to be the graph of tan theta. And this is theta on that axis, right? It's just like that. Now, tan theta, you can think of it as sine over cos, but I think it's really useful to think of it as the gradient of the line. So if you just think about the pen, when we're on 0, that's a horizontal line. Now, horizontal lines have gradients of 0. So this line is horizontal when theta is 0. So tan 0 must be 0. Also, if we get round to pi, you can see, we've spun around, you can see we've got another horizontal line. Horizontal line means tan theta is 0. So that is also 0 there. And then if we go back around to 2 pi again, so we've done a whole cycle, of course, we're at 0 then. So we know we're passing through these 2 points. Now, if you consider the points that I just skipped, so at pi by 2, you can see we have a vertical line. Now, the gradient of a vertical line is classically undefined. Also, you could think about, well, this was sine theta over cos theta. So when theta is pi by 2, cos theta is 0. So we're dividing by 0. So it's another reinforcement of the fact that tan pi by 2 is undefined. We have a vertical line here at pi by 2. And at 3 by pi by 2, so tan theta is undefined at both of those places. Asymptote. So we have a vertical asymptote when we divide by 0, as in cos theta is 0 at those points. So here and here, right? So once you get those in, you've done the hard bit really. We've got the zeros and we've got the asymptotes. Then we need to think, well, what happens between these? So if you just think about your line, well, and actually I'm just going to add one more line because this gradient analogy works well. Now what I'm doing, I'm drawing the line x equals 1, right? So if you think about tan as gradient, remember gradient could be change in y, as in the y step, for unit change in x, as in change of 1 to the right, in x, right, basically. So because this is a unit circle, well, this is a length of 1 as we go from here to here. So if say this theta that I've drawn, if I just extend that, well, where it hits that axis, that is the value of tan theta at that point. So you can see here, we know that tan 0 is 0, but as we can see, the gradient's increasing as we go around. It's going up and up, and it's not going to stop increasing all the way. So imagine if I extended this line here until it hits this line, well, that's going to be quite a high value. And you can see when it gets towards that asymptote, you can see the gradient's going to be really, really big. So it's going up to infinity there. So what's going to happen? This gradient's going to slowly get bigger, and then it's going to really get bigger and approach an asymptote, right? Then we need to think about the other side of the asymptote. So the other side of the pi by 2, we start with a really, really high but negative gradient. So really, really high. So it's going to start down here. Imagine if we're approaching pi by 2 from the other way, you can see we're approaching a really, really high but negative gradient. And then we come round and it goes gradually to 0. So we start from a really, really large negative gradient. When I say that, imagine this line, so that's the line like that. If we extended this until it hit this line, well, that's going to happen way off the screen, way off the board, and it's going to cross this line at a really, really large but negative value. So it's going to go down here, and then it's going to come up to 0 like that, and it's going to bend off down there. The other side of the pi, well, we start at 0, and we go down to here, when you can see that line has a positive gradient. If we extended this line until it hits this, it's going to happen at a very, very high value. At this line, just before it's undefined, it's going to be really, really steep and positive. So it's going to go from here from negative gradient all the way up to a really, really steep gradient. The other side, from the pi by 2, we start off with a really, really high negative gradient. Again, just imagine extending this line until it crosses this line, and just reading off the value, it's going to be minus a lot. So it starts off really negative, and then it just gradually gets less and less and less until it goes to 0. So something like that. When I say less and less and less, I mean the actual numerical value. Obviously the gradient's increasing because it's going from negative to less negative, but the actual magnitude of the gradient is getting less. So that is one cycle of tan theta, and then that will just repeat. Remember, tan has a period of 180 degrees, so if I have just kept this going, if I showed you more of the domain, or this graph, this would just happen here, and this would just happen. So what you just get this repeating wiggle here, and then asymptote, asymptote, and then it happens again, and it happens every 180 degrees.